Welcome back, everyone. We are now to chapter 4, and we're going to talk about some things that we can actually do with the derivative that we just learned about in chapter 3. So most of chapter 4 is going to be some form of application of the first derivative. All right, so let's jump into it. We're going to talk about maximum and minimum values, and we're going to start with absolute maximum. And absolute minimum. Value of f on D being a disk or the domain value. And when we talk about minimums and maximums, we are talking about y values. So this is the value of f, or f of x, which is y. And so in this case, you can see right here, we have an absolute minimum. So a parabola comes down, it bottoms out at its vertex and then continues on up. And in this case, there is no absolute max. Because we can see it actually goes up to positive infinity, so there is no absolute maximum. Now, in this case, for this function here, we have an absolute max at 4. So 4 is the absolute maximum, and we say that there's an absolute maximum at x equals 2. So when x equals 2, y is going to equal 4, and that's the absolute maximum. We also have an absolute minimum. And that looks like the absolute minimum is 0, and that's specifically at x equals 0 in this case. Now, these are two nice solid dots that we can see here. Here we have open dots, which means for us that they're actually, this one is supposed to be solid. Let's fill that in. And this one is not. So here we have, again, an absolute max, which is 4, specifically at x equals 2. But because we have an open circle here, there is no absolute minimum. And for this last one, we have open circles, there's no absolute maximum, and there is no absolute minimum, because we have open circles on both ends. All right, so let us continue on. And here we're going to say we have a local maximum. This is a local maximum now. Or a local minimum. Again, these are values of f. On D, now we're in the domain, and relative to our local max or min, we're always, so our f of c is where we have our maximum, and all of the y values are going to be larger than all the other y values when we're close to c. So you can see down here, at c, we are at an absolute max. And when we're close to c, all of these x values are going to give us y values that are smaller than this maxed out point right here. Is basically what that's saying. Now here, we have, actually, I'm going to change that to, when we're near C, we have a minimum, a local minimum. So that's down here. I'm going to call that D. And notice it dips down. And for all of these values here, so that's a D. For all of these values here, as we're close to D, D is going to be the smallest of all the other y values that are near there. That's what the definition is saying there. And so we have a local max here. And you'll note, and this is important, that the tangent line at these points has a slope equals 0, which means f prime at c equals 0. And here we have a local minimum. And once again, the slope of the tangent line right there is once again 0. This is where m equals 0, and we can say f prime of d is also 0. And when we have something kind of weird, like here at E, we don't have, f prime doesn't exist, but we do have a local max. So there is a local max. However, by the way, this is also the absolute max of the entire function. We can see it's the highest point total. So it's very possible that there can be an absolute and local max or min like we have there. And I just want to point out that f prime does not exist here. And they called this a corner in a different lesson that I gave. That means that the derivative doesn't exist there, but we still have a local maximum. Now, I want to point out that the absolute minimum is right here. And you can see it's the lowest y value of any other y value of this particular function. All right, let's talk about Fermat's theorem. If f has a local max or min at x equals c, then f prime of c equals 0. All right, and we are going on the assumption that f prime of c exists. If we meet this condition here. And I want to point out here that we have what are called critical values here, here, and here. Which can form critical points. Now, the value just means we have the x value. A critical point would mean we have the x y value, meaning we have the actual xy ordered pair. All right, let us continue on. So we have another definition here. We have a critical point, a critical value actually, of a function is a number c, which is in the domain, meaning it's an x value of f, such that either f prime of c, that should be prime there, f prime of c equals 0, or f prime of c does not exist. And we saw that does not exist here, like when we have what's called a corner. All right. If we find a critical point where the derivative is 0 or the derivative is undefined, is that going to be a minimum or maximum point? The answer is no. Not necessarily. It could be. Critical points are candidates for local extreme. Local extrema means a local min or local max. And we have a quick little example down here. We have, in fact, let's graph x to the third, just to get an idea of what we're looking at here. x to the third looks like this. And you can see we have a slope of 0 right here at 0. So we have this slope here is m equals 0, specifically at x equals 0 in this particular case. And we can mathematically find that by finding the derivative and setting it equal to 0. And you can see, dividing the 3 out, taking the square root, we get that x equals 0. So we have a critical point at 0, 0, but it's not a minimum or a maximum. Or extrema. That's how we would word that. All right, we are on to the next page. Find the critical points of f of x equals x squared times the natural log of x on 0 to infinity. Now you'll note in this case that we're not including 0 because we can't take the natural log of 0. We can only use positive values for that. So we're going to have to use chain rule here. Pardon me, not chain rule. We're going to have to use product rule. And to be clear, the x squared is my f. Well, I guess it'd be g and h because we already have f of x. And so here we go. If prime of x is going to be 2x ln of x plus x squared over x, which of course reduces to just x. So this is 2x ln of x plus x. And what we're going to do is we're going to set that equal to 0. I'm going to go ahead and factor out an x. So this means x equals 0, but x cannot equal 0. So it's out. This also means ln of x equals -1/2, which using some logarithm tricks, we're going to get that x is equal to e to the -1/2. And there is our critical value. This is our critical value. And if we wanted the critical point, I'd have to find the y value. So that'd be f of e to the -1/2. That's going to be x squared, which x in this case is e to the -1/2 to the squared, ln of e to the -1/2. And this will become, you'll notice 2 times 1/2 gives me a -1, so that's e to the -1 times, and because these are inverses, they completely cancel one another out. So the y coordinate in this case is a -1/2e. So my critical point is going to be e to the -1/2, comma, -1/2e. All right, this next one gets a little messy. Find the absolute minimum and maximum values. Now, when we're on an interval like this, in fact, this note here, to find the absolute minimum maximum on an interval, this is specifically when we have an interval, we need to test the endpoints. So the endpoints, in this case, we need to know also when x equals -1 and when x equals 2. Endpoints of the domain and critical points. So I need to test at x equals -1, x equals 2, and at whatever critical values I end up with here. So once again, we're going to have to do a product rule and set the whole thing equal to 0. And I'm going to put minus because when I take the derivative of this function, I get -1. So negative x to the 2/3. And we're going to set that equal to 0. This should be 1/3, pardon me. All right. So let's multiply through by 3 just to get rid of that. And I'm going to multiply through by, actually, I'm going to factor out and let's multiply through by the 3 first. Get rid of the fractions. This is going to be 2x to the 3rd at -1/3 times 2 minus x minus 3, because I multiplied through by 3, x to the 2/3. Again, equals 0. I'm going to factor out an x to the -1/3. Now, that's going to be as though I were dividing by a 1/3 there. So this is going to be x to the -1/3. And I'm left with 2 times 2 minus x minus 3x. Third, keep doing squared. All right, which means x to the -1/3 is going to equal 0, which means that x has to equal 0. That also means, let's distribute this. This is going to be 4 minus 2x minus 3x equals 0. This is going to be 4 equals, that's -5x, moving that over, it gives me 5x, x equals 4/5. Now we have a problem with this. Actually, this is not true. This becomes 1 over x to the 1/3 equals 0. And if I multiply both sides by x to the 1/3, this means that 1 equals 0. So this is nothing here. So our only critical value, this is our critical value, is here. So we need to test 3 points. The 2 endpoints, so let's we're going to see what we get here. And so let's do f of -1. So -1 to the 2/3 power times 2 minus -1 becomes +1. And x to the 2/3, -1 to the 2/3, I should say. Let me show you just real quick. That actually becomes -1 squared, which is +1, and then 1 to any power is always 1. So that's going to be 1 times 3, which is just 3. Meaning my critical point here is going to be -1, 3. Let's now find f of 4/5. And I'm just going to dump that into the calculator and get a decimal approximation, because we're going to end up with a crazy radical here. So let's just type this straight in as it is. So 4 divided by 5 raised to the 2/3 power. You may need to use parentheses with your calculator. And that is going to be times 2 minus 4/5. 2 minus 4 divided by 5. Yeah. So this is about 1.034. So this is our point. 4/5 comes 1.034. And our other endpoint is f of 2. This is going to be 2 to the 2/3. 2 minus 2, which is 0. So we have the point 2, 0. Which means our big conclusion here is because 3 is the biggest y value that we've run into, This is the absolute max on this interval. And because 0 is the smallest y value, this is our absolute minimum. And this is potentially a critical value. Remember, it's just a candidate to be a critical value. It's not necessarily a critical value. We'd have to take a look at the graph, but we're not analyzing that now. We're going to do the same thing for this one here. And we're going to have to test the endpoint -1/2, the endpoint 4, as well as any critical values that we're going to run into. So let's take the first derivative, set it equal to 0, and see what we get. So we're looking for critical values here. I'm going to factor out a 3x. And it looks like we're going to have critical values at x equals 0 and at x equals 2. So we are going to have to test out -1/2, 0, 2, and 4. And whichever y value is the largest and the smallest, those are our critical values. So let's start here at f of -1/2. And I'm getting 1/8. You can verify that. So we're looking at the point -1/2, 1/8 as our, that would be our endpoint here. Let's do f of 0. Equals 1, so we have the point 0, 1 as a potential critical value. F of 2. And for f of 2, I'm getting -3. So that gives, so that's going to be 8. That's going to be 4 times 3 is -12. So 8 minus 12 plus 1 is going to give us our -3. So we have the point 2, -3. And we have the point, we have to test the other endpoint here, f of 4. And I'm getting 17 with that one. So 4, 17. So we're only looking at the y values to make this determination. So it looks like we have an absolute minimum here. And we have an absolute maximum here. And again, that's within this interval. If we didn't have that interval, we would have a harder time figuring what the minimum and maximum are. And it's possible that they don't even exist. I hope that was helpful.